Okay.
All right.
Hi.
And then you're
One more time.
you're listening to
Keyboard and Quill.
From StarTree,
Creators of the Real-Time Analytics Summit.
And
podcast.
I'm Tim Berglund.
I'm Rachel Pedreschi.
In today's episode of Keyboard and Quill, we're going to look back at how we got from the mainframes of old to the cloud of today.
Hey, Tim.
Yeah, Rachel?
When was the last time you installed a program on one of your personal computing devices?
I install apps
Yeah.
on my phone. That's a thing. But like the download and install software thing, that feels a little old-timey. I'll do it sometimes, like, say, a video editing program update. That's a somewhat unusual hobby.
That is an unusual hobby.
I've got some. But yeah, the download and install motion does feel a little bit like a thing of yesteryear.
I tend to install extensions into Chrome, and then when I get a new PC, I need to install Chrome, which I always forget about.
Mm-hmm.
And then I'm like, got to install a browser.
Yeah, I mean, it's interesting how much of our electronic life is lived through apps on our phones or just straight up tabs in Chrome, websites.
Yeah.
We use them for travel, personal finance, romance, shopping, news, talking to friends, arguing about politics. And that's all in devices, right? And that device you're using is doing something. It's showing you stuff, but is that the software you're actually using? In what sense is it? Or more to the point, where's the data? All the stuff that we're putting, where is it?
And I mean, no offense to floppy disks, but I'm not even sure that my children know what a floppy disk is.
Yeah, ask them why is this, what's the shape on the save icon? I don't know, that just means save.
But you're right. What is going to happen if you're not connected to this internet, which gives us access to this amorphous cloud thing?
Yeah, not much of your actual work is happening in a comprehensive sense locally on the device. You're connected to the cloud, and that cloud has a long history of how it came about.
And you're not talking about the ones in the sky, I assume.
I am not. I'm talking about the one that is that amorphous blob of computing resources that's off there somewhere that we all talk about and don't always quite know what we mean. And there's a lot of factors that have to come together to get us the cloud that we have. We've been exploring some of these.
We have, a lot of them.
In the show so far. Let's focus today on some of the things that had to happen.
Hey, Jeff, why don't we warm up that time machine?
There's that, maybe you've heard of it, Antikythera mechanism.
Speaking of time machines.
That's right. That device features heavily in Indiana Jones and the Dial of Destiny.
It is the Dial of Destiny.
It is
It's like the original time machine.
The time machine. Yeah, it's pretty cool. It was discovered in a shipwreck underwater, this geared
No way.
thing. Yeah, 150 BC, this Greek machine, probably for computing astronomical events or something like that.
That's a lot earlier than I think people realize.
It is, yeah, and much more sophisticated than was widely believed those folks were able to do with metalwork and stuff. But it was an analog computer. And Europeans in the 1500s and 1600s are starting to get good at watchmaking and things like that. And there were some folks who tried to make mechanical calculators. Blaise Pascal tried to make one. Leibniz apparently made one. And
in order to calculate longitude, they needed a portable timekeeping device.
yes, yeah, exactly.
John Harrison put together basically the predecessor of a wristwatch.
Yes, a precise clock. So
Right.
Europeans are getting good at making stuff like that, and so they're trying to make mechanical calculating machines because science is ramping up and becoming more quantitative, and astronomy, and there's all this arithmetic and blah. But
just watching the phases of the moons of Jupiter isn't doing it for people anymore.
it's it's not a certain kind of person. Which brings us to really 1819 London. So Charles Babbage was this wealthy nobleman, scientist guy, and he was obsessed with the problem of calculating numerical tables. I've seen some of these, actually. So early, in the 90s, early in my engineering career, I saw a book on an electrical engineer's shelf that was then an old book that he had as a relic.
Right.
But it was tables of logarithms to 5 digits.
Oh, interesting.
Yeah.
I remember using that a little bit in high school.
Yeah, and so in the slide rule era, you'd look up the table, the number of the table, set your slide rule, and do the math.
Yep.
And you had to crank all these out by hand, which was error prone. the printing process was error-prone. And Babbage's errors, no, I could have a machine do this. In fact, I talked to Professor Doron Swade, who is a very, very interesting guy. He's got the background of an engineer and actually became a historian to pursue this question of Babbage. And we're going to talk to Doron more in a future episode on the evolution of analytics. But he's a specialist in Babbage, and he had this to say about his motivation for building the difference engine, this machine he was trying to build.
The start of automatic computation is when Charles Babbage and his friend John Herschel, 1821, were checking manually calculated astronomical tables. That they became increasingly dismayed by the number of errors. And eventually he became exasperated, as it were, clasped his hand to his head and said, I wish to God these calculations would be executed by steam. And steam was a metaphor for the infallibility of mechanism and also as a symbol of production. You could make tables at will if the calculations were done by machine. The purpose of Babbage's difference engine design was to calculate and tabulate mathematical tables of great generality.
So he wanted to do this. He built some prototypes and, of course, famously never got it done. His design actually did work, though, and Dr. Swade was part of the team who in 2002 finished building an actual working difference engine that worked exactly as designed. Babbage never saw that happen in his lifetime.
Oh, that's unfortunate for him.
It is. There's again, Dr. Swade, fascinating guy. And Rachel, there's so much going on here at this very early stage because he's trying to automate computation. And what he sees is we got to produce these tables of numbers. I wish we could produce them perfectly. Let me make a machine that can crank out some numbers. And for the mathematically inclined, it could find the roots of polynomials. That's what the difference engine did. If you don't know that math, don't worry. It was just a big machine that had gears and very steampunky, and because he wanted to produce these lists of numbers.
So you're saying for roots of polynomials, like basic algebra type of computations?
Yes, only higher degree than you did in 7th grade. It was a bigger pain in the butt to do all the math. And that was his vision, and that failed. His critics said the problem with the errors in these tapes, it's not that big of a problem, honestly. You find one every once in a while, you figure it out, you fix it. We're kind of fine, and your big, giant, expensive thing, I don't think we need it. So, time came, he couldn't close his next funding round, and never happened.
And how does Ada Lovelace fall into this? I thought Ada Lovelace was one of the first programmers.
Ada Lovelace was a collaborator and correspondent of Babbage. They wrote letters back and forth. And she was the one who I think really understood what he was doing. There's apparently nothing in his writing that indicates that he saw anything more than a calculating machine to crank out numbers. And she was like, oh yeah, what even is a number?
Very deep.
You could assign a number to a note and you could make this machine compose original music. Maybe not this machine.
Right.
Once you've got computing machines. So there's this fundamental insight she has that she had, I don't think Babbage did. There's no reason to believe in the record that Babbage had it. You can assign a number to any concept. A letter can be a number, a musical note can be a number, and now all of a sudden this computing device can do things other than logarithms to 6 digits, as cool as that is.
That is pretty cool. So you're saying that we have Ms. Lovelace to thank for ChatGPT?
Indirectly, she's got the vision for what a computer can do. She's always credited as being the first programmer, and she did have a paper that she published where she had a difference engine procedure. But interestingly, in getting some background on this, Babbage had those, here's some procedures for how I can configure my difference engine thing to do stuff, published before Lovelace, but he always did it. So calling her the first programmer might not quite be right, but the first person to actually see what computers could be, that's her.
She's like the first VC visionary.
Yes. I don't know if she was the money backing for him necessarily, but certainly a very important person in the history of computing. The other thing is just about startups and new ventures. And the guy was trying to make a computer.
Right.
That turned out to be a good idea. But the use case he identified, I don't know if it really needed to be solved. That's the interesting thing.
We've seen that, though, haven't we? Where people have been playing around with these concepts because they're hobbies or they're something that they're interested in to see how these projects could be used to solve real life problems or improve people's quality of life.
Yes. And the use case he had in mind just wasn't compelling enough to spend the kind of money that
What do you
people
mean?
wanted to spend.
I love logarithms to 5 digits.
I know, they're great and actually very important, especially to science of the time. But yeah, they already had them and they were good enough. It didn't matter. And Lovelace's vision ends up being the one that prevailed.
So speaking of use cases, by U.S. law, I don't know if you know about this, but U.S. law says that a census needs to be done every 10 years in the United States.
Yeah, it's in the Constitution. It's law of the land.
Because that's how we set up our Congress with Senate, House of Representatives. Very important for the system of checks and balances that we have in the U.S. But counting people can be hard. And in 1880, they actually found this to be a really hard problem to solve because they were 8 years into the counting of the 1880 census, so 1888, and they didn't see an end in sight. They weren't going to be done counting the 1880 census by 1890, and they had to do another one in 1890. Luckily, this guy named Hollerith came up with a tabulating machine. It was electromechanical, using relays, solenoids, poles of mercury, and punch cards. I just visioned this thing in my head. It seems
I would love to have seen one. Actual literal pools of mercury and little things that stick through a hole in a card. And how cool is that?
just epic. But it basically counted the number of holes on punched cards. So it didn't use binary. It used these pools of mercury to count the number of holes on those punched cards. But in the decades that followed, that tabulating machine company merged with other companies, as they tend to do,
Yes.
becoming the Computing-Tabulating-Recording Company in 1911.
Has quite a ring to it.
It does. It's the CTR company. And funnily enough, do you know what it was renamed to in 1924?
I think I could guess, but I don't want to.
International Business Machines, or as we know it today, IBM.
So some of the roots of IBM are in the counting of the 1890 census, which is the first one to be done through some kind of automated mechanism.
Exactly.
It's kind of cool.
Yeah. So in the 100 years or so after Babbage is a period of innovation in the electromechanical card punch, reading, sorting, and tabulating machines. So this was all humming along, quite literally, fairly well. But they really didn't do everything that we think of in a modern computer.
After a short break, we'll see how these tabulating machines turn into the first mainframe.
I'm Rachel Pedreschi.
I'm Tim Berglund.
This is Keyboard and Quill. We're going to keep going with our show on mainframes. I would say that mainframes are probably the first computer that we can recognize today, that we can go back and say, yeah, that looks like what we use today.
And the development of those early machines, it's super interesting for me as a tech person looking at them, like how much like a computer that I recognize does that need to be? Like the widely recognized quote unquote first computer is Colossus, 1943, Bletchley Park in England, that's somewhat north of London, and it was the machine that Alan Turing and his team built to decode German messages.
Again, they had a need, and they were able to utilize some of the innovations of the time and add to them and make them work for a very pressing need in this particular case.
And this is a case where it's not like,
Just life or death.
yes, it's life or death. There's Babbage is saying, this would be cool and it would be better and I could get this one error out. This is not that. This is, we absolutely need to do this thing. Build a device that can do this thing.
And I think that's a turning point where we now become reliant on something that looks like a computer to be so important to life.
Yeah, to the survival of the Allied nations. So that's a computer, but you don't program it as such. It's built for hardwired to do those calculations.
Okay, so this is not COBOL style.
There is absolutely not. And in 1946, You've got a programmable computer called ENIAC, great name, the Electronic Numerical Integrator and Computer, by these two professors, Mauchly and Eckert. It was programmed by plug boards.
Yeah, tell me about these plug boards.
Well, like telephone operator, switchboard, the old-timey thing where you've got all these cables and you're plugging one in here and one in there. So, the good old-fashioned room-sized things that's taking 150 kilowatts of power. And it was a computer, though.
Right. And probably made of things like vacuum tubes.
All vacuum tubes. That was a key innovation. That's what, like a 40-year-old technology now, but absolutely necessary for these things to function.
At least it's not a steam engine.
It's not a steam engine. And 5 years later, in 1951, Mauchly and Eckert take off and start a company.
Do they do it in their parents' garage?
I think that came later.
Okay.
When these things happened in California. But they made a machine called UNIVAC, the Universal Automatic Computer. And they made 46 of them over the life of the company, which was a lot.
That sounds like a lot.
Yeah.
And who bought these 46?
Big companies and the government. UNIVAC and the era of the mainframe has launched.
Are they still using vacuum tubes?
They were, but in 1959, IBM launches their mainframe, the 1401, fully transistorized.
Why were transistors important? Why were they a better choice than vacuum tubes?
Smaller, cheaper, more reliable, lower power, better in every possible way.
So I guess that means that if the computers are cheaper, that means that more people can have access to them, right?
Yeah, it's still like 46 UNIVACs. That's not very many. And when you get to the 1401, over 12,000 of them were made during that product's lifetime.
That's a massive difference.
Uh-huh.
I'll need a computer made out of not vacuum tubes to figure out the percentage higher than that is a 46.
Yes. You could do it on paper, but it would take a while and it would be error-prone. And Charles Babbage could not handle that. So yeah, and I've actually seen one of these in operation at the Computer History Museum in Mountain View, where I live. You
live at the Computer History Museum? That does not surprise me at all.
That's very funny.
Why have I not shocked
They have a really nice cafe there, okay?
And how does your wife feel about this?
She came with me to the demo, and we both typed our names in the card punch, and it printed them out, and I took a very cute selfie. Anyway, yeah, they've got a restored 1401, and it was a pivotal machine, because even at 12,000, that's still not very many, but now you've got this order of magnitude expansion in how many companies can have one of these things, right? You don't have to be the United States government or the biggest bank in the world or something like that to be able to justify it. I sat down with one of the guys who worked on the 1401 originally.
Oh, wow, that's really neat.
Yeah. Oh, it was so much fun to talk to. His name's Frank King, and I was trying to get a sense from him really what this machine meant to people at the time.
The 1401, it's really the computer that was affordable. A local power company couldn't afford a computer, so they used business machines like tabulators and collators. And if you think about this, just think of all the data in the world was on cards, on IBM cards. And the 1401 was responsible for making the card go obsolete, to change that to magnetic media. So all of a sudden the market changed. Everybody was trying to build things that would put this on tape or would put this in a computer, and we were in dire need of programmers. And I hated programming.
I feel you, Frank.
I have been programming since I was 10 years old, and I very much identify with that statement. You know what I don't hate?
What don't you hate?
I don't hate video games.
I would say that was probably the killer app of the time.
Yes. And oddly, it took a long time. 1960. There was a machine made by Digital Equipment Corporation called the PDP-1, and the first video game called Space War was created on that. I've seen a remake of that on a computer my dad bought in 1981, and I didn't know that I was looking at something that historically important at the time, but it's pretty fun.
I bet you my kid's VTech watch could probably play that video game now.
Oh, yeah. Oh, absolutely. Yeah, no question. These two little spaceships orbiting a star, they could shoot missiles and shoot a little laser at each other.
Oh, how cool.
It's great. The missiles would also orbit.
Is that the same deck as like the old deck alphas that I used to work on?
Yes. Digital Equipment Corporation. And around this time, 1961, you have the first all-electric desktop calculator. It was a British product called the Anita. Allegedly, that was something like a new inspiration to arithmetic or something.
Oh, wow.
With those really beautiful Nixie tube displays. And so all those previous electromechanical calculating machines finally vacuum tubified.
We were back to vacuum tubes.
Yes.
When did those hit transistors?
That's a good point. That should have been a transistor machine. For whatever reason, it wasn't, but that's a good point. Yeah.
So the progression here is that computers are becoming cheaper. There are more and more applications being developed and run on these computers. Smaller companies are able to buy them. But they were also becoming more powerful that you were able to rent time, or as they called, time sharing. And I'm not talking about the timeshares that we now pay thousands of dollars to try to get out of.
Right. Or, I would like you to come to this 90-minute presentation and I'll give you a free expensive dinner. There's no obligation. Not that kind of timeshare.
Not that type of timeshare. No. But multiple people could be using a single computer at once. But this only really made sense with the advent of terminals, which were becoming a commercial reality in the early to mid-60s. Now, this was after television, but just after television, right? Being able to use the same technology that we were entertaining ourselves with, we could also use to be able to interact with a huge supercomputer.
Yeah, with a big computer at work. Those were the good old-fashioned green screens, or some of them were kind of amber,
Right.
Just text. You could type on a keyboard. Those keystrokes would go into the mainframe and it would send characters back to you to look at. But it was still interactive, right?
But it was very job-oriented. You had data, you brought it in on tape or punch cards, you ran code on the data, you got output, you ran jobs.
Yeah, it was a batch processing world. And it's not like absolutely everything was batch. This isn't really so much our story today, but it is important to note communication. We talked about telecom recently,
Right.
and so much communication is electronically mediated now at this point, in the 60s broadly, that intelligence organizations can gather signals intelligence, can kind of eavesdrop on communications.
Oh, right. Changing the world of the spy industry.
Yeah. But they're able to acquire much more raw data than analysts can process. And so that has created for government and intelligence applications the requirement to process real-time streams of data. So we tend to view that, Rachel, you and I, as a recent innovation. And in the mainstream information technology, it is.
But it makes total sense that it was happening earlier.
Yeah.
There was telephones, there was telegraphs. All this information was happening in real time that could be collected. And the faster they could process it, the more timely the information that they would have.
Yep, absolutely. So that stuff was happening then in a very specialized way.
And what was IBM doing around this time? We haven't heard from them for a while.
Cranking out mainframes. In the early 60s, this big bet the company kind of project, the System 360.
Was it successful?
It, in fact, apparently was.
Okay.
Yes. It was a new mainframe platform, and it's the first time there's now this computer platform that has an operating system. What's cool is software that was written on those 1964 System 360 machines, to some degree, that can still be run on modern IBM. I think they're called Z series, the mainframe now. We're kind of talking through mainframes and what's going on in computing as we're thinking about how we get to the cloud. There's a lot of important things happening.
Actually, you could leverage this, right? And say, hey, this is a user application, right? That's still so important that we use it today.
Yeah.
So
Yeah.
this is just kind of like Ada Lovelace's vision, right?
There are more things going on. She said of the difference engine, this is a new kind of thing. There hasn't been a thing like this before that can automate mental work. And it's going to change things in ways that are going to be difficult to see. And most people, I think, in the 60s thought, oh, these are big things for doing scientific calculations or data processing. Arthur C. Clarke, who you may recall from a previous episode, was the guy who first imagined a geosynchronous satellite and was, at this point in the 60s, a sci-fi author. He had this to say. He's standing in a computer room, and the person giving the interview is there with his son, and Arthur C. Clarke is imagining the future of computing.
I brought along my son Jonathan, who in the year 2001 will be the same age as I am now.
When he grows up, he will have in his own house, not a computer as big as this, but at least a console to which he can talk to his friendly local computer and get all the information he needs for his everyday life, like his bank statements, his theater reservations. This will be in a compact form in his own house. He'll have a television screen like these here and a keyboard, and he'll talk to the computer, get information from it, and he'll take it as much for granted as we take the telephone.
I wonder though, what sort of a life would it be like in social terms if our whole life is built around the computer? Do we become a computer-dependent society?
In some ways, but they'll also enrich our society because it'll make it possible for us to live really anywhere we like. Any businessman and executive could live almost anywhere on Earth and still do his business through a device like this. And this is a wonderful thing. It means we want him to be stuck in cities, we better live out in the country or wherever we please, and still carry on complete interaction with human beings as well as with other computers.
That is jaw-droppingly visionary.
It is incredible.
Prescient.
Yes. However, not even Arthur C. Clarke could foresee post-pandemic return to office orders, but still pretty solid. And there was even a subtle shade there. He said you'll have at least a console in your house where you can talk to your friendly neighborhood computer.
Sounds like Alexa to me.
It sounds like the cloud. Because my first impulse on hearing that is, no, Arthur, you have a computer in your house. Look at my laptop. I've got this powerful computer. It's not quite like that. And then I think, no, actually, that's sort of what we're talking about today, is
exactly
that, in fact, it is like that. Because this computer I have here is really just to make pretty pictures on my screen. A lot of the work is happening somewhere else, and that's the transition we're trying to work through. Yeah, so all that brilliance was 1974 when he was giving that quote. Let's rewind a few years back to the 60s. Here's another documentary helping the American television viewer imagine what life will be like in the future with computers.
Something like the Home Shopping Network?
I think so.
Fingertip shopping will be one of the many homemakers' conveniences. This video console will be channeled into the store of her choice. There, a camera will scan a display of wares, which she will select by push button. What the wife selects on her console will be paid for by the husband at his counterpart console. All bills and transactions will be carried out electronically. A central bank computer will debit the family's account the amount of purchases and credit the department store, for example, informing the family's home computer at the same time. Father, at the touch of a button, receives an instantaneous printed copy of his budget, the amount of taxes he owes, the payments left on the car, and so forth. Also at his disposal is an electronic correspondence machine, or home post office, which allows for instant written communication between individuals anywhere in the world.
I don't know whether or not to be insulted or amazed by that clip.
Yeah, or maybe just a little bit of both. Rachel, you were talking about the what was your?
TI-85.
TI-85. Okay, I was going to say another number. This is because I am just a few years older than you, and we didn't have those. I did have access to my dad's HP 41CV programmable Hewlett-Packard calculator, which used reverse Polish notation for arithmetic, as all calculators should. And in terms of looking back at where calculators are going, HP in 1968 launched the 9100A programmable desktop calculators, this big hulking thing, bigger than a laptop, but programmable. And here's a voice from the early 1970s describing what that might do.
The heart of the classroom system is the 9100 computing calculator. It can be used as either a very simple to operate calculator or a very powerful desktop computer. It is a completely self-contained unit made up of a keyboard, a cathode ray tube, and within the case, the electronics package. Solutions to problems can be programmed at home by students using cards that are marked with a pencil with codes representing instructions. When a card is run through a reader, it programs the computer in the same manner as done with a magnetic card. This allows freeing of the computer for greater utilization by a number of students.
In addition to mathematics, algebra, and physics, the classroom calculator system has many useful applications in chemistry, biology, and economics. The availability of computing calculators, small enough and inexpensive enough for classroom use, has opened up exciting possibilities in creative teaching. Forward-looking educators are carefully studying these opportunities.
That actually reminds me of a type of desktop computer similar to the calculator that I had in the 90s, and it was a word processor.
Yes, a special purpose little computer.
And fun story, I actually won that word processor on a game show, on a kid's game show.
Really?
Yeah.
What did you do?
I was on Funhouse, and I won a bunch of stuff, including a word processor. And I remember it had like a little orange screen, and I would type in my reports, and I had a little not-so-floppy disk that I could save. Yeah.
Is that episode on YouTube by any chance?
It is. I'm still very good friends with Joe.
Sammy, who do we have for the red team?
Well, we have 12-year-old Rachel Pedreschi and Joe Sanfilippo. Yeah!
This is it, man. This is your chance to run through the funhouse to capture a whole bunch of cash and prizes. But first, let's show them exactly what they can win in the funhouse today. Tiny?
Well, Rachel and Joey, two of you can score the Video Writer Word Processor, a self-contained writing system with keyboard, screen, memory, dictionary, and printer.
That computer was actually a word processor. I mean, it was a computer, but it was a word processor.
Yes, there was a processor in it, and it was doing compute. Okay, that was absolutely amazing. Do you know what became of the host? What he's up to?
J.D. Roth? No idea.
Does he still have a mullet?
No, but my partner Joe is a very successful voice actor.
Really?
Yes.
You still in touch with him?
Oh yeah, all the time.
That's fantastic. And you know, Rachel, apart from game shows,
yes,
and that was amazing. There was a phrase that clip used about the calculator. It called it a desktop computer. If you want to look up, just Google HP 9100A sometime. If you're just burning with curiosity, you'll see a picture. Doesn't look like what you'd think a desktop computer looks like. And we're going to come back to that phrase in a few minutes. That's an idea whose time is coming.
That's actually why I brought up the word processor, because it was a type of desktop computer, by the way.
It absolutely was. It wasn't a computer in the sense that we think of one, but it's certainly a computer, and it certainly sits on a desk.
For sure.
And again, folks are seeing more than mere calculation happening. Ada Lovelace saw a new kind of thing. She actually described the difference engine as being unlike any kind of object that had existed before, since she saw the potential of kind of computing in the abstract. It wasn't just a slightly cooler thing to do with a steam engine, a mechanism to hook up, but something potentially novel in human history. And in this mainframe era that we're entering the 1970s now, some companies are starting to make slightly smaller mainframes that they call mini computers.
But with bigger bell-bottom pants on?
Yes, brighter colors.
Right, okay.
Just more exuberance overall. Yeah, and so very famous machine, 1970, the DEC PDP-11. Remember the PDP-1? We were talking about video games before?
Yeah, I do actually,
Well, this is the 600,000 of this machine sold. So cheaper, higher volume. These things are proliferating. Lots of different kinds of companies can get one of these. And this is the machine, slightly techie detail here, but this matters. The original version of an operating system called Unix was written on the PDP-11. Remember, we're talking about how we get to the cloud.
Yep.
The machines in the cloud use a descendant of that very same software from that machine in 1970.
So it sounds like there's a little bit of, I hate to use the word, but democratization of the use of computers within organizations.
Yes. That's a relentless trend here, but you really see it starting to happen. After a short break, we'll see how these computers are talking to each other. But first, let's replenish our in-game currency.
At the tone, please record your message.
Hi, this is Brittany from Fremont, California. Keyboard and Quill is made possible by StarTree, host of the Real-Time Analytics Summit, an annual conference that brings together professionals in the data space to discuss harnessing actionable insights from real-time data. Join us to learn, teach, connect, and have an amazing time with the best community in the user-facing real-time analytics world.
Register now at rtasummit.com.
I'm Rachel Pedreschi.
I'm Tim Berglund.
This is Keyboard and Quill. We're going to keep going with the advent of data communications.
What is happening now with more computers in more parts of the business, if you're a large business, you've got sections geographically distributed, you've got computers that need to talk to each other. So we've got telecommunications networks, easy to make a voice phone call to anywhere at this point in the developed world. But how about data? That's a new thing. You've got data records in one computer that need to get to another computer. I spoke again to Frank King about what I would have called data communications, using a somewhat old-timey word. Frank calls it teleprocessing.
I said, what I would like is really teleprocessing, because that's the thing where all the really good problems are. Teleprocessing is computers talking to each other. For example, a Sears would say, okay, who's overstocked on this? And they checked their inventories, but in their warehouses, and kept up with it. When you went into a Sears store, you ordered something that they didn't have. One of these warehouses would put in, we can get it for you tomorrow, we can get it for you the next day, or whatever. That was the great time to be alive. You could solve problems for them, and they were thankful for that.
Ooh, computers are getting fancy.
Yeah, and connecting them to each other. And people are coming up with standards for computers to be able to talk to each other and ways of linking machines. And he talked about it like it was still a pretty elaborate thing where you had lots of problem solving to do. He talked about noisy lines and error correction.
Have you ever tried to build a distributed app over any type of network? I think it's still pretty complicated.
It definitely still is, yeah. But there were a lot of problems that we don't solve in the kind of tools we use to make computers talk to each other that he was solving on the front lines. It was pretty cool.
That is very cool. So what was one of the first examples of these computers talking to each other? What was a use case? We keep coming back to what is the thing that made this widespread and available to everybody?
Yeah, that people actually wanted. And he was talking about inventory management in a retailer. But what interests me is the standards, like not the one-off, I made this computer talk to that computer, but the standards that show up. And if you've ever read anything about the history of the internet, you've probably heard of this thing called ARPANET. In 1969, that's the Advanced Research Projects Agency network.
We really don't make acronyms like we used to.
They're so good. Famously, this network connected some academic sites and some military computers. And the idea was, instead of this one-off, let's carefully engineer this connection from this computer to this computer, it was sort of a loose connection of networks where you could add computers to it, take them away. It's sort of a flexible networking of networks together.
So you're saying the government is what? Did this to us again?
Yes. Well, this is actually a pretty good thing. This worked.
I'm not knocking it. They just seem to be the ones, strangely enough, that keeps the innovation moving in the early to mid 20th century.
Yeah, on the leading edge of research like this, you need somebody with a big and expensive problem. And we were talking about the census in 1880.
Right.
Who else is going to have a problem that size, right?
And in this case, the Constitution told us that we had to do it.
Had to do it. So here we are. Yeah. And militaries. And you get these other, back like in the early 50s, the early computer users tended to be banks, airlines, just things that had utilities at giant scale.
And had a lot of money.
And had a lot of money to spend, yeah. That ARPANET led to the first appearance of the term internet, first published appearance of that term, 1974.
That's much earlier than I think most people realize.
Yes. Most people would probably say like 1990, was it? Or when was pets.com?
Yeah,
right.
AOL.
Exactly. This was 2 years after the publication of Me. You had a riveting document called RFC 675. Definitely Google that and read it. It's great.
It must be so much fun at parties.
I'm great. Yeah, really. Let's talk about TCP. Now, so yeah, it was an important document for the people who are actually building the network, those engineers and all that stuff. It was a protocol for transmitting packets. We were talking a minute ago about error-prone networks and things that can get dropped. This was like a protocol to make sure nothing gets dropped, even if there's errors. Vint Cerf, Stanford University, and Bob Kahn at DARPA published this paper, and they were the first ones to use the term internet.
If we discuss the future too much, what we end up doing is talking a lot about individual futures and how the cloud is going to start to begin to permeate even more of our lives than it already has. And in our world, your and I's world, the cloud is already 100% permeated.
Yeah, which gets us to a good stopping point for this episode.
Because, boy, that's a lot to read.
It is. Please don't read RFC 675 unless you really, really want to. But we'll take this up in the next episode with the advent of the microcomputer.
So small in size, yet so big in possibilities. I'm Rachel Pedreschi.
I'm Tim Berglund. We'll see you next time. Many thanks to Frank King from the Computer History Museum, Bill Inmon, the father of the data warehouse, and Dr. Doron Swade from the Royal Holloway University of London. You can find links to their work in the show notes.
Our show is produced by Peter Furia, Noelle Gallagher, and Tim Berglund. It was written by Tim Berglund
and Rachel Pedreschi. It was edited by Noelle Gallagher and Peter Furia, and our amazing original music and sound design were created by Jeff Kite of The Voids.
Keyboard and Quill is made possible by StarTree, hosts of the Real-Time Analytics Summit. Register now at rtasummit.com.
You can subscribe to Keyboard and Quill for free wherever you listen to podcasts, including Apple, Spotify, and YouTube. Please leave us a comment and a rating if you have a minute. And if you're a data professional, you should check out the Real-Time Analytics podcast, which we launched in early 2023. New episodes every Monday, link in the show notes. I'm Tim Berglund.
And I'm Rachel Pedreschi.
See you next time.